I am not Neil James, as you can see, and I'm not as comfortable at the stage as Neil James. But, just to introduce you to the team, Rob James is well known in this fraternity, and he was supposed to be here, but he suffered quite a nasty heart attack a few weeks ago. So he's bound to his home for the next few weeks, and hopefully his surgery is scheduled for the 7th of July. Myself, I'm Hattingh. I'm a mechanical engineer. My knowledge on fraction mechanics is very limited. I see myself as an application engineer, so that the talk you'll see this morning is very much an applied talk, and very little high-end results. Then Dave Asquith is from Sheffield, Ireland. He's a young academic that was involved in a lot of the residual stress measurements we've done. Mark Newby is an engineer within ESCOM, which is a power utility in South Africa, mainly vibrations and measurement engineer, and then Philip de Bel, who is an international welding engineer. Just to give you a brief outline of the talk, and I'll try and look around the corner here. Knowledge equals safety. That is the philosophy that we really use. And then the three questions that we're trying to answer is, what knowledge is necessary to ensure safe operation? Why focus on the residual stresses? How does knowledge of residual stresses and their magnitude assist in combating fatigue and fracture? Now, most of the work I'm going to present you this morning is related to power industry, and maybe the next slide will tell you why. If you look at those two slides, I come from a developing country, South Africa, and we've got a major problem with power shortage. And we can blame a lot of people for that. You know, politicians, finance ministers, whatever the case may be. But at the end of the day, we as engineers have to solve this problem. 27% of our running plant currently is older than 40 years. Okay, that sounds pretty bad. If you look at America, 28%, so it's not that bad. But if you look at the big blue area, the 20 to 40 year area, this is the 66%, this part here. This is where we are really now have to think on our feet, trying to keep turbines, generators alive, and the steam side of our industry. So it presented some unique challenges, but also some unique opportunities. And hopefully through this talk, you'll see how we took knowledge generated a few years ago to assist us to make quick solutions. Right, this is the type of things we want to avoid. This is an explosion of or failure of a 600 megawatt steam generator. It's still within design life. Failure of a fairly route, you drop a 21 kilogram blade at 3000 RPM, and it destroys your whole generator and unit. Total damage, about 100 million euro. Everybody's upset about that. But if you go deep and you look what's happening in the rest of the world around turbine failures, then you will find that over $1 billion per annum is related to turbine failures. So it really makes the work that we do on turbines and the residual stresses to prevent fracture very relevant. Trying to set the scene, and you'll see the next few slides, you'll see Neil James' hands in it. The main drivers, I always say, is cost. To replace a 600 megawatt unit, $2 billion. It's a lot of money in a developing country. In most cases, we cannot afford it. We're going to have to come up with other ways to do it. Most of our generating capacity in the world is 30 years and older. And we have to take cognizance of that. I don't know how many of you are aware of what's happening in your power generation industry, but certainly keep an eye on that. So major overhauls and refits is an inevitable component of life extension. This is where your research data, fracture research, fatigue research helps us as engineers to make a decision on how to solve these problems. Now, the current group of authors you've seen there, for the past 10 years, it's not something that would happen overnight. For the past 10 years, we've worked quite actively in repairing and finding repair techniques and analyzing, you know, what we do to structures when we repair it. And we've settled down on using a friction process repair technique. So the two parts that's important for us is sampling. And when I'm saying sampling, I'm not talking surface sampling, I'm talking invasive sampling. I'll show you some case studies around that, because we need that information. The next point then is, once you do invasive sampling, you need to repair, and I will cover some of that issues there. Residual stress is so that weld repair and cladding of power stations is a big focus of our research work. Right, achieving the required extended service life for expensive industrial components is what drives us. So we need to have appropriate fracture safe and fracture reliable design philosophies. We have to have critical, I want to call it in-critical service condition monitoring, because as soon as you make modifications, your condition monitoring ability must go to the next level. Fracture mechanics-based assessment to detect defects and to understand their influence. Weld repair is a big part that our life goes around. When you do a weld repair, you upset the structure, you induce unwanted residual stresses, and you have to know what you do. Assessment of residual stress levels. We know that manufacturing processes induce high levels of residual stresses. We have to control that. Effect scan, and in most cases the effects of residual stresses is overlooked by engineer designers, and we only really discover that a bit later in our life when we start having failures. And remember, we're working with components now designed and delivered in the 1970s. The technology available to the design engineers is not at the same level as it was today. Magnitude of and distribution of residual stresses and the modification that they undergo is important to us. And then residual stresses can make life prediction complex. This is something that I've learned over the last few years, and that is that if you look at codes, and welding codes, and you want codes to guide you around how to work with residual stresses, they're very generalized. And you need to really do a lot of experimental work to get an understanding of your residual stresses. Numerical simulation needs to be calibrated. Luckily now we've got abilities around synchrotron and neutron diffraction where we can measure quite large components, and I think Phil is somewhere, Professor Withers, somewhere in the audience. He did a lot of work 50 years ago in getting engineers to understand how to use neutrons and synchrotrons, and to measure residual stresses. And we've really hopped onto that bandwagon, and it helped us a lot, as you will see in the case studies. The rest there you can go and catch up on the paper. Going back to the failure I showed you earlier, the failure there was caused by a fatigue crack through a fir tree. We did extensive work on ID15A and the ESRF, looking at unpinned roots, new pinned roots, ex-service pinned roots, and the final finding there was that the pinning process, although we all know that pinning introduces compressive residual stress, it will prevent the crack from forming. In this case, when you do pinning of a complex shape, it's not that easy. And somehow the coverage were uneven within the complex parts of the fir tree, and that just a slight miss at one place caused a fatigue crack and a 600 million euro failure. Right, so residual stress and condition monitoring is an integral part of fracture mechanics based life assessment. And this next point for me is very important. Supports run, repair, replace decisions. Well, that is the decisions that engineers sitting in power plants have to make on a daily basis. They haven't got the luxury of running to a lab for 3 months and do experiments. We have to have valid information and tests to be able to make a decision on to repair or replace. Now, if you want to replace a turbine, it's not that easy. It's an easy decision to make, but usually there's a 2 to 5 year waiting time for a new turbine. And sometimes if you've got a power utility that's in trouble, you cannot do it. You have to think of other ways to extend the life of that. I'm not going to go through the rest. The first case study I've got here for you is a repair of fingerpin blade attachment holes. We detected cracks on these discs. Did our fracture mechanics calculations, did our 3D FEA work, saw that the cracks are not critical, but they will be critical at the next shutdown. So you're sitting with a crack that you can tolerate, but within a few months' time you're going to have a solution on the table. The photographs at the bottom just there to show you the complexity of the curvature or the attachment of these blades. So what is the problem? These three problems that you sit with in this typical turbine is incorrectly drilled holes or spaced holes, hole validity, the second middle picture there, and then the last one is cracks. These cracks could be fatigue or it could be stress corrosion induced cracks. So we come up with a proposed repair procedure. Conventional welding cannot be used, so we make use of friction hydropillar welding. And so the first photograph there, or the first picture, we drill out the damage. Then we put in the backing plate, yellow backing plate. We then drill down in the backing plate. And the reason why we're going down in the backing plate is that the place for introducing defects within the process is at the interface between the consumable tool and the backing plate. So we take that area away. We do the weld, do your post-weld heat treatment, machine excess material away and drill the hole. And this is the proposed solution that we came up with. Right, you have to take into consideration that you've got a complex shape, so you need to get to the finger in the middle as well. So by that we just decided that we'll drill out the hole at the top slightly bigger, work through, repair the hole in the middle, and then repair the hole on the outside. So repair that one, and then you can just re-drill that hole there. The process we use is based on friction hydropillar processing, a process that was invented by TWI. Right, so it's not that simple. There's a number of issues that you have to consider. Number one is you have to develop and optimize the welding process. It's not something that just happens. We've done at least 200 welds before you've actually had a welding process with parameters that gave you the right weld quality. The nice thing about this process is an automated weld, so consistency is very good. Assess the microstructure, mechanical properties, and the residual stresses. I will give you an idea how we've done that. Then design, manufacture your platforms and do industrial trials. And only then you can implement the process as a solution within the industry. This is what we've done with the residual stress part. We've welded 5 samples. 3 of them as welded. The first one we cut up into D0 samples. The second one we left undrilled. The third one we drilled an 8mm hole through. And then we had 2 samples that we did post-weld heat treatment on, and one drilled, one undrilled. So that was, remember, you've got a week of being time. You have to get all of this data through. So you rather take less samples than more samples, but make sure that your data is valid. Or if you go to SALSA, instrument at the IL in Grenoble, and you make your measurements. Now, the reason why I put this slide in, you have to take great care in making sure that the samples that you take to the ILL is representative of what's going to happen in the real life. If you miss this point, you're going to have to sit with data that is misaligned with what's happening in the field, and you've not solved a problem with respect to your repair. This is the welded samples we've made, and again, the first step is your sacrificial vacuum plate that we put in. Then your sample goes in, automated welding process. So the weld there is a program weld. By this stage, you've sorted it out. It's now pushing of a button, the weld gets made, and then finally you've got your weld. Alright, that's the matrix we've used to measure. I'm not going to go through that. Just simple 3 levels of stresses that you quantify. But in this graph, what I'm showing you here is 2 sets of welds. It's the W2 sample and the W5 sample. Now the W2 sample was the as welded, and the W5 sample was the as welded post-weld heat treatment. And I think the positive thing there is that you can see as welded, we sit with 500 MPa tensile residual stresses at about 15-60 millimeters away from the center of the hole. Whereas after heat treatment, you reduce that considerably to about 100 MPa. So now we're happy that we can manage our residual stresses, and we can start implementing the process in the power or onto the turbine. Alright, so in summary, what have we achieved there? From peak tensile values in the Z direction of about 500, we went to very low values. By drilling the hole, once you've drilled the hole, you end up with this positive residual stress. Tensile residual stress is on the inside of the hole, but they're of the magnitude of about a 40 MPa. So you're going to have to realize that you sit there with the tensile residual stress that you have to deal with in some other way. Then post-weld treatment of the specimens decrease the magnitude of residual stresses at all positions. Blade repair successfully accomplished. The next case study is one that is taking off quite exponentially at the moment. And again, it's around, if I can get a piece of material, the core that you see there is about 25 millimeters long, and it is 8 millimeters in diameter, and it comes out of a steam line of 40 millimeters thick. So I've got a piece of material now that has got 50 years or 30 years of history inside it, and it can tell me a story. But by taking that out and getting that history, I need to repair the hole, and that's what this is about. Right, so what can we get from that? We can get macro, micro structural information. We can get tensile, static strength information. We do a lot of small punch screw testing currently for industry, because we do that on an 8 millimeter disc, half a millimeter thick, that we cut out of this at different places. We do a lot of fraction toughness using the inverse finite element analysis and small punch test. That's just another hour talk for another day. Right, the weld core process that we've developed, for this process, I think important to note, we've got an ASME proof. Our generation petrochemical people will not allow you to touch the equipment if you don't need your process ASME proof. So we've got that ASME proof. There's the code case number if you want to use it. But simply, what do? We core, take a core out. That's really the piece we're after, and then we repair it by a solid state welding process, not a conventional welding process. For the sake of time, I'm going to go a bit quicker. In South Africa, 5 years ago, 10 turbines, end of life, had to be replaced. There's no way we can take 10 turbines out of service. So and the German manufacturer indicated area of concern is on the pull face in that area, and all the models showed end of life, severe creep damage. And you have to believe this. Unless you can show it is not the case. So what we've done is we've then developed a process whereby we say that we know that we're confident with our friction hydropillar repair process. We now need to convince the people that we can take a sample out and repair it safely. So if you look at what we've done here, we've developed some backing inserts that goes into the T-slot there, and we after that little red piece of material sitting there. Because it's a through hole here and we need backing for our process, we have to put backing in. All of that is sacrificial, that can be machined away afterwards. Develop your platform, put it in place, and not much more, but this still sugar. It's a coring stage, you get the core out. Now from taking the core out of the turbine, within 4 to 5 hours, we have the answer from the metallurgist saying that this is the creep damage, the turbine must be reworked, the turbine must be scrapped, or it can go back into service. So the total process within a question of 2 days, including in the longest is your pre and your post-weld treatment. Within 2 days we can get a decision whether the turbine can go back or not into service. That's the extracted hole, and what you're seeing here is the repair process. Interesting here is the residual stresses that we've done. Because we're very careful, we did residual stresses on that's the repair side. Blades put back, repair side, we did residual stresses by XRD on the surface there. Now look at the neutral data, the red and the blue, and then the green line here is our XRD data. Now that gives you confidence. You've now done a repair, and your residual stresses on the surface is more or less what you saw in your experimental work and your samples, and you now, confidence is high, and you carry on. Right, so sample extracted provided crucial creep condition information, direct measurement of creep damage and other material processes with calibration of FEA modes. That is very important. All that creep data that we got now, that actual creep data, we could send back to the OEM and say, right, go and recalibrate your models whereby you predict the creep life. So that is very important. So this has now become a very important tool for us in managing the remnant life of our turbine fleet within some of the power stations in South Africa. Currently, we've applied the process to 5 identical turbines, 5 out of 10, 4 out of the 5 returned to service. Another 6 is one we had to scrap, and most of them, the creep damage was so shallow that we could machine out the groove slightly bigger, machine it out without any adverse effect to the stress within the turbines. Right, the last one I'm going to go and talk to you about is laser well build-up of turbine blown shroud tenons. I was not involved with this project, so I'm a bit cold here, but I think the next slide shows you what happens. You've got turbine blades and they've got these tenons. They put a shroud over, then they rivet these tenons over. So when you have to do blade inspection occasionally, you have to grind the rivets off, take the blades out, and scrap the blades. And you cannot put them back because the tenon is now too small. What we've done in this case is, and that part you can go and read in the paper for the sake of time, it's just the laser welding specifications. We made a number of samples to take to the ILL. Laser welded tenons onto it. We had a sample as welded with post-weld heat treatment, and post-welded heat treatment and machine sample, and we quantified the residual stresses on that. You can just see the setup within the ILL. There's the tank, and you have very high triaxial residual stresses at the fusion boundary on both sides of that laser weld. So really, immediately from this data, we say we've got a very high risk of cracking. However, if you heat treat these samples properly, you can get the residual stresses normalized in a certain way. And again, now the confidence that you've got a process that is sound, homogeneous, and of which the residual stresses is understood well, you can apply. So again, this we have not applied in industry, but you know, when times arrive, we are ready now to implement it. Some case studies that Prof. James put in here, and I'm going to really just skip them because of time, but the one that I think is important is the specific one where when you machine casting, you get distortion, and that distortion results in fretting fatigue. It's a residual stress issue. This embrittlement here with flame cutting, incorrect welding processes, it's a residual stress phenomenon. This is a 14-foot diameter cast grid gear that was weld repaired. The fatigue crack grew slightly away from the weld repair because of not the weld repair, but your support ligament is affected by the residual stresses. You can read the details on that in the paper. In conclusion, then, sampling and repair is a cost-effective part of condition monitoring for thermal power plant. Automated friction tape hydrophilic process is a powerful addition to refurbishment and life extension procedures. Lower values of residual stresses, fewer defects, potential for development of fully automated technique for bespoke repair procedures, lower cost. 3D measurements of residual stresses are an essential part of structural approach to combating fatigue and fracture. And it is really easy to get large samples into places like the ILL. Learning from history, particularly important to pay attention to possible causes of residual stresses. Design process must actively seek to combat fatigue and fracture. Proactive condition monitoring is likely to require detailed information on residual stress level. And finally, many industrial cracking problems in large and expensive structures arise from residual stresses issues. Could be avoided. Knowledge of factors that influence fatigue. Make sure you get them underneath. Understanding effects of welding on alloys, critical. Full sharing of relevant information between all parties in a contract. We tend to underestimate that how important the paperwork is, and then realization that the technique to minimize residual stresses and defects should be consciously adopted. And then the last quote is, those who cannot remember the past are condemned to repeat it. That was said by some Spanish philosopher. Right, acknowledgement. Beam time at Salsa.